Hello everyone. In this video, we're going to talk about right triangle trigonometry. Some of you may have seen right triangle trigonometry before in previous math classes, like if you took some geometry or trigonometry back in high school. So in trigonometry, we're really studying angles and functions of these angles, but it all gets started with triangles, and in particular, these right triangles. Remember, a right triangle is a triangle in which one of the angles is a 90-degree angle, and we always denote that special 90-degree angle in a right triangle with that kind of corner box. And so here I have a couple different right triangles drawn on the board for us to look at and analyze. And what's special about all these triangles is that they are all what we call similar triangles. So we say that two triangles are similar if their side lengths or the triangles themselves are proportional. But an easier way to think of that is two triangles are similar or proportional if they're just the same triangle, but different sizes of the same triangle. The idea is if we were to kind of magnify or zoom in on this orange triangle enough, if we got close enough looking at it, it would look exactly the same as this green triangle up here. And so we can just see from the pictures here, even though they are not drawn perfectly to scale, but we can still see from the pictures that the smaller triangle is going to have a smaller side length, corresponding side length that is, when compared to the larger triangle. However, one thing that is exactly the same for both of these triangles is the angle between their side lengths, right? This angle we're going to denote as theta. That's just one of our Greek letters that is commonly used to denote one of our angles. We already talked about our right angle here. That is our 90-degree angle. And then we have a third angle, which we could find if we wanted to. We're not going to need that for our discussion here. And if we did need to find that third angle, we can use the fact that all the angles in a triangle, and this is true even if it is a non-right triangle, all the angles in a triangle have to add up to 180 degrees. So this missing angle would just be 180 minus 90 minus our known angle of theta. So one of the very important observations that gets this whole ball of trigonometry rolling is that there is a unique relationship between our angle theta and the ratio of the side lengths within the triangle. So let me go ahead and clarify what I mean by this. So let's go ahead and assign some side lengths to these right triangles just to give us something to talk about. So maybe this small orange right triangle has a base side length of 3 and a height of 4. Well, then we could find that remaining side length that we call the hypotenuse using our Pythagorean theorem. Right? Remember the Pythagorean theorem, a squared plus b squared equals c squared. Well, if we do that side work off to the side, we should find that our hypotenuse here has a length of 5. Well, now let's go ahead and suppose that our green triangle is similar to our orange triangle. That's what we were talking about earlier. And let's go ahead and say it's just twice as big as our orange triangle that we started with. Well, if it's twice as big, then the side lengths are going to be twice as long. So that base side length will be 6 instead of 3. The height will be 8 instead of 4. And the hypotenuse for that longest side length will be 10 instead of 5. Right, and we can still verify that the Pythagorean theorem holds, and this is a right triangle. And so now that we have some values involved, we can go ahead and clarify what we mean by this statement that we just made. So there's a unique relationship between this angle theta and the ratio of the side lengths of our triangle. So what that means is if we take any ratio of the side lengths for these corresponding or similar triangles, like this side length divided by this side length, that would give us 8 divided by 6 for that ratio, which simplifies to 4/3. Well, if we take the same corresponding ratio on the similar triangle with that same special angle theta, then that ratio will also be the same. Height to base gives us 4:3 or 4/3. And there's lots of different combinations that we could make here for these ratios, right? We could do 6/10, 6/8, 10/6, 8/6, and find the matching ratio on the similar or smaller triangle, and we'll get the same decimal value when we evaluate those ratios. And so what this means for us is that there's got to be some special connection between this angle and those ratios. And that's where our trigonometric functions come into play. All our trigonometric functions are the ratios for a special angle within a triangle, or at least that's how we will initially define them. Eventually we'll expand the definition so it'll still work for these right triangles, but work for larger angles like those that we would not find within a right triangle. So like I mentioned earlier, there's 6 combinations in the ways in which we can take these ratios between any 3 side lengths of a triangle or a right triangle. And that's how we're going to define our 6 basic trigonometric functions, just as these 6 different ratios that can be taken from the side lengths of a right triangle. All right, so we're just about ready to make a table listing these 6 trigonometric functions, what their names are, how we denote them using function notation, and what their definitions are for these special ratios for these side lengths of our right triangles. But we need a little bit of terminology before we jump into these definitions. So let's go ahead and get that up on the board. And this terminology isn't anything too complicated, but it's important for making sure we have our ratios set up correctly and our trigonometric functions well defined. And we've already started to use some of this terminology, right? One of them is the hypotenuse. So the hypotenuse is the longest side length in a right triangle. That's always going to be opposite the largest angle in our right triangle, which is opposite the 90-degree angle. So longest side length in a right triangle is our hypotenuse. And now these other 2 side lengths don't really get special names like the hypotenuse. They're labeled with respect to the angle that we are working with. So this side length that is on the side opposite of our angle theta is what we call the opposite side of our triangle. Or we're going to refer to it as just the opposite side length, but technically it's really the opposite side length with respect to our angle of theta. And then this bottom side length is what we call the adjacent side length to our angle theta, or just the adjacent side length for short. And so one last thing to note before we jump into these definitions I've been talking about for a while now is these side lengths are labeled with respect to our angle of theta. And so if we're working with this angle up here, maybe let's just call it like beta or something like that, then we're still going to be talking about our trig functions that are upcoming for this angle beta instead of theta. And we'll have to kind of relabel our triangle a little bit. The hypotenuse will stay the same. That is still the longest side length and all that. But now the side that was adjacent to our angle theta becomes the side opposite to our angle beta. And similarly, the side that was opposite to our angle theta turns into the side that is adjacent to our angle beta, or that other non-right angle in our triangle. The point of that is just be a little bit careful when you're labeling the opposite side and the adjacent side in your right triangle. Make sure you're labeling those with respect to the appropriate angle, the angle you are working with. All right, so now that we got that terminology out of the way, we can go ahead and define our 6 trigonometric functions. And we're going to go through all 6 of them carefully, but really 3 are going to have a lot more attention paid to them. Let's go ahead and start with those 3 most popular or maybe important trig functions or ratios. And so the first trig ratio or function is what we call the sine ratio or the sine function. So it's S-I-N-E, that's how you spell the name of this function. But if we're going to denote it using our function notation like f of x or f of theta, the way our function notation for sine works is it's S-I-N, and then this is our parentheses for our function notation used to indicate the input. So the input of our sine function is some angle theta, and the ratio is going to be the output of our sine function. So what is the output of our sine function? How do we define it as the ratio of some side lengths in our right triangle? Well, it's always the opposite side length of our angle theta, although I'm not going to write that of our angle theta part because that takes up too much space. And we have to divide the opposite side length by the hypotenuse in our right triangle. And so you can remember sine as the ratio of the opposite side length to our input angle theta divided by the hypotenuse of our right triangle. And maybe some of this is ringing a bell for some of you that have seen some right triangle trigonometry before. What we're kind of coming up with right here is that popular acronym SOHCAHTOA. So let's go ahead and get the ka and the toa in SOHCAHTOA out of the way next. Our next important trig ratio or function is called the cosine function or the cosine ratio. In our function notation, it's denoted as cos of our angle theta, or we read this as cosine of theta. And the ratio definition of our cosine function using side lengths in a right triangle is the cosine function is the adjacent side length divided by the hypotenuse. All right, so our next trig function, right, 2 down, 4 to go, is our tangent function, or ratio. And so we denote tangent using function notation as tan of theta. Well, tangent, that's going to be the opposite side length of our angle theta divided by the adjacent side length with respect to our angle theta. Or the shorter way of saying that is tangent is opposite over adjacent. Right, and so now we got SOHCAHTOA on the board. Just in case you've never seen that memory device before, because right, not all of us have seen right triangle trig before, this is just a nice little way to kind of quickly remember the definitions of these 3 most important trigonometric functions, right? SOHCAHTOA, that's for sine, cosine, and tangent. Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, right? So these are the 3 most important trig functions, the ones that show up and get used most often. There are 3 others. Let's go ahead and talk about those briefly, and we'll also talk about why they're not as popular as sine, cosine, and tangent. All right, so now we have our 3 remaining trigonometric functions or ratios up on the board along with our first 3, and those last 3 trig ratios, our functions, are called our secant, cosecant, and cotangent ratios or functions. They're denoted using SEC of theta for secant of theta, CSC of theta for cosecant of theta, and COT or cot of theta for cotangent of theta. And how do we define these trigonometric ratios? Well, the secant ratio is the hypotenuse divided by the adjacent side length to our angle theta. Cosecant is hypotenuse divided by opposite, and cotangent is adjacent divided by opposite. And so what we can notice looking at these last 3 trig functions or ratios when compared to our first 3 is that really they're almost the same thing, or at least they're storing the same information, right? What I mean by that is if we compare our tangent and cotangent functions together, well, the ratio that we get out of tangent is opposite over adjacent. Compare that to the ratio we get out of cotangent, adjacent over opposite. They're the same ratio, just reciprocated or flipped over each other. And that is basically the main reason why we don't have to worry about this cotangent function too much. If it does show up, we can always work with tangent instead, just using that reciprocal relationship between our functions. So we're going to go ahead and write down what we call these reciprocal identities on the board now, but don't worry about them too much at the moment. They'll kind of be combined and collected with all of our other identities as we discuss them. So let's go ahead and start with our secant function. Right, secant is hypotenuse over adjacent. That looks a lot like our cosine ratio or function, but cosine is adjacent over hypotenuse. So if we were to flip cosine over, take the reciprocal of that, or look at 1 over cosine, that would give us the reciprocal ratio and give us hypotenuse over adjacent, or secant of theta. So the idea here is secant of theta is exactly the same as 1 over cosine of theta. We already mentioned this about tangent as well. Cotangent is the same as 1 over tangent of theta. Cosecant is hypotenuse over opposite. If we flip that over or take the reciprocal, we'll get opposite over hypotenuse. That is our sine function. So cosecant of theta is equivalent or can be swapped out with, interchanged with 1 over sine of theta. And all these reciprocal relationships or identities work in the opposite direction as well. What I mean by that is sine of theta is the same as 1 over cosecant of theta, and so on. Cosine of theta is the same as 1 over secant of theta, and tangent of theta is the same as 1 over cotangent of theta. So these reciprocal identities are going to help us kind of rewrite some of our trig functions in terms of our others. The way it usually works, although this is not a hard, fast rule, is we might have a bunch of secants cosecants, and cotangents showing up in an equation or an expression. And we can use some of our reciprocal identities over here to rewrite them in terms of our more favored sine, cosine, and tangent functions. This will make simplifying some expressions easier to work with. It'll also make solving some equations easier to do. And so we're going to want to dedicate all 6 of these trigonometric functions to our memory. The way I like to do it is I remember sine, cosine, and tangent using SOHCAHTOA. Unfortunately, there isn't a popular memory device for secant, cosecant, and cotangent. We could try it. What would that be like? Sha, cho, cow. Just doesn't roll off the tongue as well. So I remember SOHCAHTOA for sine, cosine, and tangent. And then I remember these reciprocal identities to help me evaluate secant, cosecant, and cotangent. So the way my brain works is if I want to take secant of some angle, and we'll do an example of this in just a minute. But if I want to take secant, instead of remembering secant is hypotenuse over adjacent, I remember secant is 1 over cosine. Cosine is adjacent over hypotenuse. Flip that over, I get secant. So secant must be hypotenuse over adjacent. The important thing, though, is we want to remember all 6 of these trig functions, and my tip is get started with sine, cosine, and tangent first. Now that we've defined our 6 trigonometric functions as ratios of side lengths for some right triangle with respect to the input or angle of interest, we're going to go ahead and do a little exercise, making sure we know how to actually evaluate our trig functions given a right triangle. And so we should be able to do this pretty quickly using those definitions we just discussed for our 6 trig functions, defining our 6 trig functions in terms of ratios of side lengths in a given right triangle with respect to some input or angle of interest that we're going to call theta in this problem. All right, so before we jump right in and find the values of our 6 trig functions, let's make sure we have our triangle set up correctly. We got our angle theta given to us. That's our angle of interest here. We have our side length of 12 and our side length of 5. It might be useful to label these side lengths as the side length opposite of our angle theta, the side length adjacent to our angle theta, and the hypotenuse. Let's see, this is our angle theta. 5 is on the other or opposite side of our angle theta, so that is our opposite side length value. 12 is not the angle opposite of our 90-degree angle, so it is not the hypotenuse. It is touching our angle theta, though, so that makes it the adjacent side. And so this, of course, is going to be the hypotenuse of our right triangle. Notice that the hypotenuse is not provided for us, and we're going to need that hypotenuse value in order to evaluate some of our trig functions or ratios. So how are we going to find that? Well, we mentioned it in one of our earlier videos. We're going to have to find that missing side length using the Pythagorean theorem. And so remember, the Pythagorean theorem says that a squared plus b squared equals c squared. That's how most of us remember it. The only one we really have to be careful about is c, though. We just have to remember that c is the hypotenuse. So another way of stating that is the hypotenuse squared is equal to the adjacent side length to our angle theta squared plus the opposite side length to our angle theta squared. So the 2 non-hypotenuse side lengths squared and summed up always gives us the square of the hypotenuse. So 12 squared, or 144, plus 5 squared, or 25, gives us 144 plus 25, that's 169. So the square of our hypotenuse is 169. If we take the square root of that, the square root of 169 is our hypotenuse length, but that is 13. So we had to do a little bit of legwork, but we found that the remaining side length, the hypotenuse of this right triangle, must be 13. All right, so now we really have everything labeled correctly on our triangle, so we should pretty quickly be able to evaluate sine, cosine, tangent, secant, cosecant, and cotangent of our angle theta for this particular right triangle. So what is sine? Well, sine is opposite over hypotenuse, so it's going to be 5 divided by 13. Easy, done. We already got our sine ratio figured out. What about cosine? Well, cosine of theta is the adjacent side length divided by the hypotenuse side length. That'll be 12/13. Up next is tangent of our angle theta. Tangent we define as the opposite side length divided by the adjacent side length. Side length opposite of our angle theta is 5. The adjacent side length is 12. So tangent of theta should be 5/12. Secant is going to be hypotenuse over adjacent, so that'll be 13/12. Notice that is the reciprocal, or just the flipped over fraction of our cosine value of 12/13. That matches up with our reciprocal identity. Secant is just the reciprocal, or 1 over cosine. Cosecant is the reciprocal of 1 over sine. So that'll be 13/5. We could also evaluate that using the definition of cosecant as hypotenuse over opposite. Hypotenuse is 13, opposite is 5. 13/5 is what we get. And cotangent is the reciprocal of tangent. So that'll be 12/5. Or you can also think of that as adjacent over opposite. That's another way to get your cotangent value.